we're going to do a hypothesis test, also called a test of significance, usually in your textbook. For another good example of this, look at the healthy streams example in the book on page 580, and there's a video to accompany that which I've posted on Canvas. I'm going to go quickly through the state and the conditions steps because I think the book example does a good job of taking care of that, but I want to spend a little more time on the calculations because the book spends a lot of time working with a table, which is not my preferred method of doing the calculations. So in this problem, we have a coffee machine that dispenses coffee into paper cups. You're supposed to get 10 ounces of coffee, but the amount varies slightly from cup to cup. Here are the amounts measured in a random sample of 20 cups. Is there evidence that the machine is shortchanging customers? In other words, is there evidence of less than 10 ounces per cup? So we are going to look at these 20 samples and find the mean of those. The parameter that we're interested in is the population mean, the mean of number of ounces of coffee in all cups filled by the machine. So our null hypothesis is that mu is 10. In other words, nothing's happened, the machine's working fine. The alternate, the one we're trying to find evidence for, is there evidence that the machine's shortchanging the customer? In other words, is there evidence that mu is less than 10? We're going to do this at an alpha significance level of 5%. Because sigma is unknown, we have to use a t-model instead of a normal model because we don't have any population standard deviation given to us. So we check our conditions. We have a random sample of 20 cups. It's reasonable that 20 is less than 10% of all cups filled by the machine. In other words, we think the machine makes at least 200 cups. And we have to check, since we have less than 30 in our sample and we don't know anything about the population distribution, we have to check. We did a dot plot, put the data into the calculator, did a dot plot, found out that the dot plot has no extreme skew or outliers, so we can proceed with a t-test. So let's get to the do step, the part where we show our computations. We first of all need to compute the test statistic. The test statistic is the number of standard deviations that our sample is from the mean of the population. So if we're saying our population mean is 10, in other words, that's our null hypothesis value, and we found out that we want to find out how far x bar, the sample mean, is from that, and we recall hopefully from our t-model before and using a confidence interval for the mean that the standard deviation of mu is the standard deviation divided by the square root of n. Now if we knew sigma, we would use sigma, and we'd use z. If we don't know sigma, we have to use the standard deviation of the sample. Now right now at this point we don't know what all these numbers are, so I'm going to suggest the best way to do this. We're going to go to the calculator, and on my calculator I have already made a list with all the coffee fill weights. I also did my dot plot here to figure out that to satisfy the condition for using the t-model. But I am now going to do a t-test on the calculator. I suggest you do the t-test first and then fill in the formula using the t-test. So doing the menu statistics, stat tests, and then going to the t-test right here, number 2. Our data input method is data. We could either use data or stats, but we are actually trying to get the stats right now. The data is a list of data. Our null hypothesis value for mu is 10. My list is called coffee, so I'm going to put my coffee in, and my alternate hypothesis was a less than 10. So when I get these values here now, I am going to copy these down. I'm going to copy down what is t, what is the p-value, what is the degree of freedom, what is x bar, what is the sample standard deviation, and what is n. I'm just going to list those on my paper, and then I'm going to use those values to fill in the work that I need to show. So here are all the lists, although I accidentally put the p-value at the end because I left it out. It was supposed to be right after t. But anyway, here's the list that I got from my t-test on my calculator. So notice I already have x bar and s of x. This is the standard deviation of the sample. This is not the standard deviation of x bar. This is the standard deviation of the sample. I would have to take this value, divide by the square root of 20 to get the standard deviation of my model that I'm going to use in the null hypothesis, or in the hypothesis test. So I can fill in now x bar and mu. I can fill in my standard deviation and my sample size, and I have my t-value, which is negative 3.49. I recommend that you double check that these numbers actually give you negative 3.49, because if your work does not match your answer, that would be a deduction for showing work. Now, what does the p-value tell us? Students are having a lot of difficulty interpreting p, so I want to go over that again. If we were to draw a picture of what these numbers tell us, this is saying when mu is equal to 10, the probability that we get a sample of 9.845, a sample mean, I should say, so this is x bar, where x bar is equal to 9.845 or less, is 0.001225. That's the p-value. So in other words, if I were to do normal CDF negative infinity to 9.845, with this being my mean and this being my standard deviation, all of this, I would get 0.001225. Or if I were to do, sorry, not normal CDF, TCDF, with my degree of freedom equals 19. So I would actually not do that. I would just use your p-value that you're given in the test. It's a lot simpler. So the p-value tells me the probability that x bar is less than or equal to 9.845 if mu is really 10. That's what the p-value tells me. This is a conditional probability. The p-value also tells me the probability that the test statistic is less than or equal to negative 3.49. So in the t model, this is my t model with degree of freedom with 1, 0, 1, and the degree of freedom equal to 19. Okay. Now let's interpret the p in words. Basically, I'm going to put this into words. There is only a 0.001225 probability of getting a sample mean fill amount of 9.845 ounces or less if the true mean fill amount is 10 ounces. So there is a conditional probability you have to have if the null hypothesis is true here. And then you have to have this is either or less or more, or in the case of a two-sided test, if the sample, you would say if the sample mean fill amount of 9.845 is this far away from 10 or farther, okay, if the sample mean is more extreme in either direction, okay, so you'd have a two-tailed test. Actually interpreting the p-value for a two-sided test, the wording is a little tricky, so we'll talk about that when we get to a two-sided test. But this is an area under the curve. It's not if it's exactly 9.845, but if it's 9.845 or less. If it was a greater than test, it would be or more. Okay, so that's really important. Make sure you get that. Okay, so what is the conclusion then? Notice the interpret the p-value is something you will be asked to do from time to time, but you don't actually have to have this in a hypothesis test. What you have to do with the p-value in a hypothesis test is do your conclusion. You have to compare the p to alpha. If p is less than alpha, basically the alpha level says I'm going to reject the null hypothesis if p is anything less than this number. So I'm kind of saying that 5% is my area that I'm saying that's pretty far away from the mean, so anything less than that, I'm going to reject the null hypothesis. This is actually much less than 0.05, so I have a pretty strong evidence here. I have very convincing evidence. I could say very convincing evidence to reject the null hypothesis and conclude. Now remember, when I conclude, I'm concluding that the alternate is probably true because I've rejected the null hypothesis. And I want to do this in the context of the problem. Okay, so I'm going to say that the mean fill amount in this machine is less than 10 ounces. The customers are probably getting shortchanged. Now, I can't say I prove that the mean fill, but I can conclude based on my hypothesis test. This is a valid conclusion. I have evidence to conclude this. Okay, now, what if I wanted to know just a little bit more then, other than the fact that I think it's less than 10 ounces? Well, I could do a hypothesis test. So I just did a quick hypothesis t interval here. I'm sorry, I could do a confidence interval. So this is a t interval. Now notice here I did a 90% interval. This is kind of a minor point on the AP exam, but it might be asked. If you do a one-tailed test where alpha is 5%, that means the 5% region is in one tail or the other, but not both. But when I do a confidence interval, I have to have two equal tail probabilities. So a one-tailed significance test at the 5% level corresponds to a 90% confidence interval. If it were a two-tailed test with alpha is 0.05, then that would correspond to a 95% confidence interval, because the 5% would be split up into two different tails. It would be 0.025 and 0.025, and so this would be 95. But with a one-tailed test, this is 90. So I did a 90% confidence interval on my calculator. I got the lower and upper bounds here that are shown. So I say we're 90% confident that the true mean fill amount is between 9.77 and 9.92 ounces. That just gives us a little additional information, not absolutely required for a hypothesis test, but if you were to do a hypothesis test to support, a confidence interval to support the hypothesis test, this is what you would do. So that's really all for this. Hopefully that was helpful.